Hello everyone, this is Mr. Kaviani, and in this video we're going to be applying Newton's second law to analyze situations involving connected objects and pulleys. Let's chat briefly about what a pulley is in the first place. A pulley is nothing more than a device used to facilitate the movement of a rope and change the direction of tension in that rope. So on the right hand side I have a little sketch here of someone using a pulley, which is really nothing more than a wheel connected to some sort of axle. And pulleys allow us to exert forces on objects in directions that might be difficult to do. So for example, if you wanted to pull this wooden barrel straight up, instead of pulling up, we could use a pulley to change the direction of tension from straight up, which is what the barrel feels. We can keep showing this arrow here. It'll just keep going through the pulley, and the person can pull on it at an angle while still pulling the barrel straight up. And so pulleys allow us to do really neat things. We can use pulleys in complex configurations as well, involving multiple pulleys to actually reduce the force needed to lift heavy objects. And we're going to be applying Newton's second law in these videos to situations involving pulleys that connect two objects that both accelerate. Before we begin solving problems involving pulleys, let's discuss connected objects. Let's assume that we're pulling two connected objects that slide over a frictionless surface shown here on the diagram. Let's derive an equation for the acceleration of the system A in terms of the force that we pull with and both masses of the blocks. Then we'll solve for the tension in the rope that connects them. We can call this here T2. We'll solve for, this is the tension in the connecting rope. If we pull with a force of 100 newtons, so if we call this T1, that would be equal to 100 newtons here. If mass 1 is 4 kilograms, this is mass 1 over here, and then mass 2 is 8 kilograms. So to begin, I'll solve this problem the same way I've solved every single problem in this unit so far. I'll draw an interaction diagram, then I'll draw force diagrams, this time for both objects separately. And I'll use those force diagrams and Newton's second law to derive an expression for the acceleration. An interaction diagram for this scenario would look like this. When drawing your interaction diagram, make sure you're showing two interactions between each block and the surface, the frictional interaction and the normal interaction. However, in this case, because we were told this is a frictionless surface, I will remove the frictional interaction between the surface and blocks 1 and 2. In this case as well, the rope tension between block 2 and block 1 is the same, so the tension in any rope is the same everywhere along that rope. So I know that the rope T2 pulls on the second block just as much as it pulls on the first block. And then rope 1 is a separate rope altogether, which pulls on block 1, and in this case the person just as much. Now, using this interaction diagram, I'll draw force diagrams for block 1 and block 2 separately. All right, in this case, on block 2, there are three forces acting on block 2. The normal force of the surface pushing up on block 2, which I've labeled as Fn2, pointing up, the tensional force in the rope connecting block 1 and block 2 pointing to the right, and the weight of block 2, or the force of gravity on block 2, Fg2, pointing straight down. I also know that's going to be equal to the mass, so m2 times g. Then for block 1, there are four forces. The normal force pointing up, the gravitational force pointing down, which is equal to m1 times g. Then the tensional force in the rope by the pulling of the person, which will be 100 newtons we were given in this problem. And then tension 2, which is the same tension in the connecting rope as it is on block 2. Now, remind myself, what am I looking for in this problem? I'm looking for T2. So what I'm going to need to do is write out the sum of forces for both objects in the x direction. Then I'll have a system of two equations and I can solve for T2. I'll show that here. Before I write out the sum of forces, I need to define a direction to be positive in my scenario. When solving problems involving connected objects, we'll always want to define the positive direction to be the direction that each object is accelerating in. So in this case, they're accelerating in the same direction to the right, but we'll see in a moment scenarios where objects are accelerating in different directions, although they're attached. So we'd want to define the direction of acceleration to be positive. So in this case, I'll just make a big arrow pointing to the right, and we'll say that is the positive direction. So for block 2, the only force pointing in the horizontal direction. In this case, the vertical directions are not important because they will cancel. The boxes are not accelerating vertically, so I know those sums of forces will be balanced. And I'm not including friction, so I don't need the normal force to solve for my frictional force. So I'll just consider the horizontal direction. And on block 2, that's just T2. Now for block 1, I have two forces in the horizontal direction, T1, which is pointing in the positive direction, and T2, which is pointing in the negative direction using the coordinate axis I've defined. Since I know that the net force is also equal to the mass of the object times its acceleration, I can write out the net force like so. The block 2 net force will look like m2 times a of block 2. And for block 1, that would be the mass of block 1 times the acceleration of block 1. Now, it's important to note that because these two objects are connected, and assuming there's no bunching in the rope, they must be traveling with the same velocity, and in this case, then also the same acceleration, since they both started from rest. So, I don't need to keep track of A2 and A1. A2 is equal to A1. In other words, the acceleration of the system is the same as the acceleration of either object. So I'm going to drop the subscript and just start calling it A. All right, so now I should see that I have two equations, right? The one for block 2 and the one for block 1. And there are two unknowns, T2 and A. And in this case, I'm asked to solve for both. So what I'll do is I'll solve this just like I solve any system of equations. I will rearrange them, one of them for one variable, and then I will plug that variable expression into the second equation. In this case, because we already have that T2 is equal to M2A, we can just take T2 and substitute in to the second equation M2A, where we would see T2. So that would look like this. T1 minus, not T2, but M2A is equal to M1A. And again, T1 is known in this case. I'll rearrange for A like so. I'll go ahead and move this M2A term to the other side so that all of my A terms are together. And that will look like this. M1A plus M2A is equal to T1. Then I will go ahead and factor out an A because I have it in both terms. And that will leave me A times the sum of M1 plus M2 is equal to T1. Then, because I'm trying to solve for A, I will divide both sides by this sum of M1 and M2 to get rid of that. And then that will give me the final expression that I've been looking for, which is that A is equal to the tension in rope 1 divided by the sum of mass 1 and mass 2. So in this case, if I were to solve numerically for the acceleration, that would be 100 newtons divided by the sum, which is in this case 8 plus 4 kilograms, giving me an acceleration value of 8.33 meters per second squared. And that's a positive, which is what we expected. It is accelerating in the positive direction. That's a good sign. Now, if I'm asked to solve for the tension in rope 2 as well, I already know that T2 is equal to the mass of 2 times A. We got that from our equation earlier. And that means that the tension in rope 2 will be equal to 8 kilograms times this acceleration of 8.33 meters per second squared, which will give us a tensional value of 67 newtons, rounding to the nearest whole number. All right, so there you have it. Now, this is actually just one way of approaching this kind of problem. Let me break down this approach on the next slide before I show you an alternate way of solving these problems. So the way I just solved that problem is what I would call the individual analysis method. And what that means is I'm analyzing each object that is connected separately. So to do this, I drew a separate force diagram for each connected object. Then I chose a common positive direction, which was the direction that both objects were accelerating. And in this case, it happened to be the same direction, but not always. Then I applied Newton's second law to both objects separately and derived two equations, one for block 2 and one for block 1 in the x direction. I solved that system of equations for my acceleration and my tensional value. While this method requires several steps in algebra in order to solve, this can be applied to any problem involving connected objects, and it is one that you should be familiar with. That said, we can use a systems approach instead of an individual analysis approach to solve for the acceleration of a system in a way that requires less steps in algebra. Let me show you how the same example would look if we solved it using a systems approach. All right, so I've gone ahead and copied over the interaction diagram from the previous time we solved this problem, which hasn't changed. This is the exact same scenario as before, but in this case, we're not going to consider block 2 and block 1 as separate objects. Instead, we're going to lump them together and treat them as what we call a system. We're going to consider them to be one large object, and on my interaction diagram, instead of highlighting separate boundaries, I will include them all in one big system boundary, like so. It's important to point out that I've also included this second rope, or this rope 2, in my system as well. And in this case, that's incredibly useful because I don't need to consider now the force of tension between the rope and blocks 2 and 1, because that is what we call an internal force. Note how it's inside of the system boundary. This T2 is inside this blue boundary. That's what we call an internal force. And when we're solving problems about systems, we only are going to consider the external forces, or the arrows that cross the blue boundary, like this gravitational force from the Earth, or the normal force from the surface, or the pulling of rope 1, T1, on block 1. Those are what we call external forces. Also, if we assume that the ropes do not have any mass themselves, then by including rope 2 in our system, we are not changing the system in a way that we can't quantify, right? I don't need to consider the mass of rope 2 when I think about the total mass of the system. I would just add the mass of block 1 and block 2. I also did not include rope 1 in my system because rope 1 is the only object that exerts an external force on the system. And so if I included rope 1, or even the person, in my system, I wouldn't have any way to solve for the acceleration, right? I need to have an external force to change the acceleration of an object. So I'm only including blocks 1, 2, and rope 2 in my system. Before I draw my force diagram, I've also gone ahead and drawn in my system boundary on the sketch to illustrate how to draw the force diagram for this scenario. If I treat M1, M2, and the rope that connects them as one big object, I can instead just draw a big force body diagram, and I can call this, right, my system. And then I'll think about all of the external forces acting on the system. So in this case, I can also look at my interaction diagram and see that that's tension 1 that the rope on the right produces, and then the normal force by the surface and the gravitational force on both block 2 and on block 1, right? Those are both separate external forces. And even though we're treating blocks 2 and blocks 1 like one large object, we still have to consider the fact that gravity was acting on them separately. So my diagram would look like this, right? This would be the force normal on 2, the force of normal on 1, the surface force that exerts on both objects. This is the force of gravity on 2 and the force of gravity on 1. So I would still show those on my system diagram, right? I would have both of those normal forces pointing up and both of those gravitational forces pointing down. Should be 1 here. And then in this case, I am not going to consider the tension on rope 2 because that is an internal force now, but I do need to consider the tension in rope 1. In this scenario, because there is no friction, these forces, right, this force is equal to this force and this force is equal to this force, and so therefore I have no net force in the y direction. If we were solving this problem with friction, we would need to take into consideration those frictional forces as well, but we'll take a look at that in another example. So in this case, my system force diagram allows me to write out a sum of forces in the x direction that looks like this, right? The sum of forces in the x direction is just T1. There's only one force in the x direction. Again, calling this direction positive acceleration. So that means that if this is equal to m total times a, right? This is the total mass of the system. So in this case, m total will be equal to m1 plus m2. Because the rope has no mass, we don't consider the rope. So that means that my acceleration would be T1 over m total, which in this case was 100 newtons over 8 plus 4 kilograms. And you'll notice that looks just like it did before, right? The same acceleration that we got when we thought of these as separate objects. And then if I were to solve for the tension now in the rope tension 2, I would need to use an individual analysis approach to be able to do that. I would have to break down, right, the block 2 into those forces that I saw earlier, right? The normal force on 1, the gravitational force on block 1. So to solve for T2, I would have to use the individual approach. That would mean that the sum of forces in the x direction, again, is just T2 in this case, which is equal to the mass of 2 times A. And A in this case is the same A for every object because they're all connected. So T2 would be equal to 8 kilograms times 8.33 meters per second squared, which we just saw was 67 newtons. So again, nothing changes about the problem. But in order to solve for the acceleration, we can take a little bit of a shortcut and call M2, M1, and rope 2 a system. That allows us to ignore internal forces and solve for the acceleration more readily. However, to solve for something like the tension in rope 2, which is an internal force, we still have to go back to that individual analysis approach, even if just briefly. So let me break down this approach, and in the next few examples, I'll use the systems approach to solve problems, as it provides a streamlined method for solving for the acceleration. So when using the system analysis method, you should draw one force diagram for the entire system. You'll choose the direction that the entire system is accelerating in to be the positive direction, and you will apply Newton's second law to the entire system using the total mass. So make sure that when you're doing this, right, you say the sum of the forces is equal to m total times A of the system, right? You can write system here if you want to as well, to remind yourself that it's for the system. Then we would solve for the acceleration of the system using Newton's second law, and then we would use the individual analysis approach, drawing force diagrams for one object at a time to solve for any internal forces if we are asked to. Okay, so as you saw, this method reduces the steps needed to solve for the acceleration of a system. And once you have that acceleration of the system, you then have the acceleration for every object in that system. And you can use this to solve for the net force on any individual object if you know its mass, which will allow you to solve for individual internal forces.